Hello class, and welcome to our first video in chapter 2.1 part 1, which is finally going to answer that first question we talked about on day 2 of class, which is on tangent lines and derivatives. So why is it so important to keep honing in on this idea of a tangent line and a secant line? And the reason is because these tangent lines help us find the instantaneous rate of change of a function that's curved. But as we had discovered that second day in class, we don't have enough information before calculus to find the slope of a line at only one point. We need a slope of a line that has 2 points, and that's where the secant line comes into play. So just to understand the definition a little bit, we think of a tangent line as a line that's touching a curve or grazing a curve or laying up against a curve without actually crossing through it at that one particular point, much like this red line is doing right here in this first example. Now that's not to say that the tangent line isn't ever going to cross the curve, because you can see in this example we would think of this part right here as being a point of tangency, because at that point the line is just touching the curve. Over here where it's crossing the curve would not be considered a point of tangency, and we would sort of ignore that when we're looking at this situation here. And look at the difference with a secant line. When a secant line is intersecting a curve at 2 points, I mean, it's literally just crossing right through that curve, okay? It's not ever grazing the curve or laying alongside or matching the direction. No, it's cutting right through the curve. Here's another illustration where it's really kind of contrasting the two things. See, a tangent line, what it will do is it'll sort of mimic the direction of the curve at that one point, which is why it sort of grazes against it. Whereas a secant line is just intersecting the function. That's all it's really doing. And so it's not trying to mimic or lay parallel to the curve at that point. Now, why do we want a line that will touch a curve or lay alongside it? Because we are going to use that slope to find what's called the derivative. So that's our third vocabulary term in this list. The derivative is the instantaneous rate of change of the function. This is the first question calculus seeks to answer, is how do you find how quickly a function is changing at an instant, right? Not over a period of time, but at one instant. How do you find that instantaneous rate of change? Again, a rate of change is just how much a function is changing with respect to x. It's how much y goes up or down as x goes right, okay? Now, how do we find that instantaneous rate of change? We find it by finding the slope of the tangent line at that given x value. Take, for example, this function here. So right here I have, well, first of all, this function is not linear. It's very curvy, right? So it has lots of different rates of change at all the different x's. But let's just focus in on this one that has a blue dot right here, this x value, which is around 0.5. Okay, we're going to focus in on that. And we want to try to get an instantaneous rate of change of this function. Let me show you something about any curved function. The more you zoom in on it, so I zoom in, I zoom in, I zoom in, I zoom in, I zoom in at that one point, look at what you see. What do you notice? That function, which was so curvy, at that one instant where I zoomed in a bunch, actually looks quite linear. We call that local linearity, where you zoom in on any point on any function and what it will appear as will be a straight line. Now our tangent line, if I can get a line tangent to the curve at this point, will mimic this rate of change, which as you can see is actually somewhat flat, right? It's not a very steep rate of change. Let me zoom back out so this would be just in normal view. So that would look something like this, right? That tangent line you see there is telling me it's following or acting like the function acts right at that point. It's just kind of grazing the curve. It kind of comes up to it, hits the curve there. They share that point in common, but they only share that point in common, and then it kind of keeps going. And what it's doing is it's kind of zooming in on that one point and showing us what the rate of change of the function is at that one point. But their line keeps going, obviously, right? The tangent line keeps going, but it's kind of showing us what this function wants to do right here. Now see how it hits the curve over here? Let's just ignore that, right? We just kind of say, well, we don't really care about that so much. We care more about what's happening right here at the point of tangency. So we can ignore other places where the line might hit the function, and we just kind of pay attention to the part where it touches it and shows us the direction of the function at that one point. So how do we go about finding that slope of that tangent line when all we are able to do to find a slope of a line is take 2 points, right? We need 2 points, change in y over change in x, to get a slope. So how are we going to do that for a tangent line when we only have 1 point on the line? This definition here is our answer. So let's take a look at this in more depth. It's worth noting here also that when we talk about the slope of a tangent line, a lot of times we also call it the slope of the graph at x equals c for the reasons we just mentioned. Because if you zoom in really far on any one graph at any one point, it begins to look linear. And so the slope of that tangent line is really the slope of the graph at x equals c. Now let's look at this definition in more depth. Let's take a look at all these pieces. Okay, so let's start with the delta x. This delta x right here is referring to a change between a particular x value c and another x value with a point on the curve. So when we say delta x, we say that's a little change in x that I would add to c to get a different x value, c plus delta x, that when I plug it into the curve would give me a new y value, f of c plus delta x, right? Would be the y value of this point right here, which is a little further down on the curve. Now, that is a secant line. So if we look at this green line, I have a secant line here with 2 different points on the curve. One of the points is c plus x, comma, f of c plus delta x. And then c, comma, f of c. That would be this point here. Now this is the point that we want to find the tangent line at. So that's why we have c plugged in here, because we want to know what is the slope of this purple line that hits the function right at the point c. But in order to do that, we begin with algebra 1. We begin with just y2, that's what this is, minus y1 over c plus delta x minus c, right? x2 minus x1. y2 minus y1 over x2 minus x1. It's change in y, which is right here, delta y, over change in x, which is right there. If you do c plus delta x minus c, well, that results in just delta x. That's why there's a delta x in the denominator. That's the change between 2 different x's, the c that we want to find the tangent line at, and then this point that's a little to the right of c. We added a little bit of change to that c to move a little to the right to get right here, so we just call it c plus delta x. And by the way, if it's easier for you, you are welcome to call delta x h if it helps you look at this limit and understand what's going on. But what I want you to understand is that delta x value is not an x coordinate on the graph. The x coordinates on the graph that we're looking at are c and then c plus delta x. Those are the x coordinates on the graph. And then these are the y values, f of c plus delta x and f of c, okay? And you see those here, y2 minus y1 over x2 minus x1. So if you were to just sort of block out, I'm just going to use a large eraser to try to block that out. So just kind of block that out in your mind. The limit, or the fraction part, so this part right here, just the f of c plus delta x minus f of c over delta x, is not the slope of the tangent line. That's the slope of the secant line. That would give me the slope of this green line, this guy right here. is what this fraction is telling me the slope of. But if I introduce this limit and I say, okay, I'll find the slope of this secant line because I'm able to do that fairly easily. But I'm going to let this change in x go to 0. I'm going to see what happens to this fraction as that second point on the curve gets closer and closer and closer and closer to the point in question. I'm going to make my delta x smaller. Well, you can kind of see with these other lines, the orange one, the red one, the purple one, and then the dark purple one, that what's happening is the point itself is getting closer to x, but the secant lines, their slope is beginning to look a lot like the slope of the tangent line. And then once you let the delta x completely go to 0, that means you're just at point C now. What you have is the slope of the tangent line. And that, my friends, by using limits, that is how we can defy algebra. Because what happens when I plug in 0 for delta x? I get f of c minus f of c over 0. I get 0 over 0, right? But what have we been learning in the last chapter? We've been learning how to evaluate limits that equal 0 over 0. This is no longer a threat. No longer a threat to us now. Limits have helped us get around. It's a loophole. I'm able to divide by 0 now as long as it's 0 over 0. This limit allows me to do that, which basically allows me to find slopes of lines at one particular point. So that, my friends, brings us to the derivative of a function. Look at this. It's the same limit that we were looking at a moment ago. The only difference is that now it has x plugged in instead of c. That means my answer is not a number. If I evaluate this limit, where I take these two generic y values on a function, the change in these two generic y values divided by the change in the two generic x values, so change in y over change in x, and I let the change in x go to 0 for any x along the curve, that gives me the derivative of f as a function of x. So in this case, your answer will be a function, but not just any function. It'll be the derivative. We call it f prime of x. That's how you pronounce this, okay? Of course, provided the limit exists. Yes. Now, this is another formal way to evaluate a derivative. I would never make you use this one by hand, so don't worry. But I wanted you to understand that this is the definition that your calculator is using to calculate the derivative. And then there's also this method. So this would help us find the derivative of f at a particular point. This limit will end up equaling one particular number, because it would end up helping us find one particular slope at one particular tangent line at one particular x value along f of x. So what do I mean by that? Let's look at this picture down here. In this picture down here, I have this particular number c. This is where I'm trying to get the line tangent. So you can kind of see that tangent line right here in blue. And I'm trying to get the slope of that line. So instead of saying delta x like we did last time, I just pick another x, another generic x along this function. So that gives me this other point f comma f of x. So here's f of x is over here. It just takes another point on this curve, and then it takes the slope between those 2 points. So it's kind of finding a slope of a secant line. So it does change in y, f of x minus f of c. That's this part right here. That's rise over x minus c. That's when you subtract these two, that gives you the distance between them. So this is rise over run, right? Just like the last slope, but only using 2 points. A very particular one at c, a given numerical value for x, and then just any other generic x comma f of x along the function. And then you take the limit of that as x approaches c. So that's still going to make the change in x go to 0, right? This is still going to become a 0 over 0 situation when I plug in c for x. because I'm making this point basically become c comma f of c. And so that is how we find the slope of the tangent line. But because it's at one particular number, then I'm only finding one point on the derivative. I'm finding f prime of c, which is a number, as opposed to f prime of x. But it's really helpful when we have to do that. It's a little bit quicker than using this process, which was highlighted here. See, this way, if we plug in c for x in this longer limit definition, that also gives us one particular slope of one particular tangent line. This alternative form is just a quicker way, a little simpler way to do it, and it would still give us the same number. Now, something that you should know for future lessons is that in order for this limit to exist, the left-hand limit and the right-hand limit of these quotients have to be equal. We already kind of know that. A two-sided limit, for it to exist, the one-sided limits have to be equal. But this will also be what we look at when we're trying to prove if a derivative exists. In order for a derivative to exist, then these limits of these quotients, the left and right, must be equal. And so we will use that in the future to prove whether a derivative exists. Now for some very important notation. So when we say derivative of f as a function of x, we could use any one of these notations at any time, and they all mean the same thing. So the derivative of f, remember, is the slope of the tangent line. Never forget that, because what is a derivative? It's the instantaneous rate of change, the change in y over the change in x at one particular point, right? Which is what a tangent line does. It lays on the function at that particular point, and the slope of that tangent line tells us what that derivative is. It tells us what that instantaneous rate of change is. So then we can say, okay, it's the limit of delta x, as delta x goes to 0, of delta y over delta x. Well, this is delta y, the change between two y values on the graph of f. So that we can also write it that way, this full-blown limit definition. But what I really want you to know is this f prime of x is what this full limit definition equals. These are synonyms. You can use them interchangeably. You could also call it y prime, because we know f of x and y are synonyms. You could also call it dy dx. This is another very common notation for f prime of x or y prime. They all mean the same thing, and they can all be used interchangeably. Or you can call it d dx of f of x. This is kind of like saying the derivative of f with respect to x. The change, the instantaneous rate of change of f with respect to x. These d's, by the way, dy over dx is really similar to delta y over delta x, but this is kind of like the 0 over 0. This is saying what you get once you fully let that delta x go to 0, which is the derivative, basically. So this notation kind of came from that, change in y over change in x, but at an instant. Once you've let delta x go to 0, you're now at dy over dx as opposed to delta y over delta x. Now these will all give you functions. These will all be functions of x, right? All these derivatives here, or all these notations. They're all the same thing, but all these notations. Now if I wanted f at a singular point, right? This would be a numerical value. These guys here are numbers. This is the derivative at a particular point. Well, you can take that limit definition you saw right here and just plug in c in place of x, right? Not delta x. Delta x is not an x coordinate on the graph. It's a change between two x coordinates, right? So never forget that. This delta x came from taking c plus delta x and then subtracting c. So it was like x2 minus x1. That's what delta x is. And then the c's cancel out, leaving just the delta x behind. So you never plug anything in for that except 0 when you're toward the end of your limit. But if you plug in c for x, you're basically locating a singular point on the graph, and what you're finding is f prime of c. This, of course, is the easier way to do that, and it's doing the same thing. It's taking two y values, y2 minus y1 over x2 minus x1, right? Slope of a secant line, but it's taking the limit of that as x approaches c. Well, as x approaches c, x minus c approaches 0, right? Because the closer x gets to c, the difference between them gets smaller and smaller. So it's essentially the same thing. The change in x is still going to 0 in this slope. Therefore, I'm finding a slope at one point, which is a slope of a tangent line, which is f prime of c, the derivative of f at c, which is a number, right? One particular value. Or you could call that y prime of c. These are all synonyms and can be used interchangeably, and they all refer to one particular derivative value at one particular point on the graph, which is one particular slope. This would equal one slope of a particular tangent line. A line tangent to the slope of f at the point c, comma, f of c. So in our first example, we're just going to kind of look at estimating, right? We always start with that in calc. I don't know if you noticed that, but we always start kind of with an estimation and then learn how to find it exactly, because it's good to just be able to read these graphs and learn how to envision their tangent line and then estimate what that slope would be. Now, whenever a graph is sort of turning around or changing direction, basically when you get to these like max or min points, like this one here, we envision the tangent line is actually horizontal there because the function's actually turning around. It's changing from having a negative slope here to a positive. So it has to kind of hit a 0 slope in between. So this first line here at the point x1 comma y1 would have a slope of 0. This second point here, which is this red dot, x2 comma y2. So if you kind of look at the curve and follow the curve and think about the slope of the tangent line, the slope of the curve, it would be facing down, first of all, because the graph is moving downward at that point, and somewhat steep because it's moving down fairly quickly. So if I just kind of draw this tangent line here, I can just take a couple points on it and kind of figure out the rise over run. It looks like it's roughly kind of going down 3 and over 2 for the rise over run, change in y over change in x. So we could sort of estimate that slope to be -3/2. Why don't you guys try this? See if you could estimate these two slopes. Pause your video and then come back to check the answer. Okay, so for part B, for the green tangent line here, that's hitting the graph at x1 comma y1. First of all, it was going down, decreasing fairly steep. I just chose this point and this point since they were easy for me to read, and I noticed that between those two anyway, it went down 5 and over 2, so roughly -2.5 for that slope. For the red line that was hitting the curve at x2 comma y2, I chose these 2 points. Again, they were sort of easy for me to read and used them to sort of estimate the slope and found it was going up 4 and over 3. So a slope of 4/3 or 1 1/3 as the approximate slope for that second line. Now, example 2, I would say, is sort of the crux of this video, where we are actually going to use the limit process to go ahead and find the derivative. So we are wanting to find f prime of x, but we're going to use the limit process in this video to do that. So a couple of things. Those of you that had pre-calc honors, I know you've learned the derivative rules, but you're not allowed to use them in this section. You have to use the limit process to find your derivative. Don't worry, we'll get to limit rules or derivative rules soon enough. Okay, so what we do is we begin by reviewing or remembering what the limit definition looks like. So this is the limit definition. And what I need to do is get an expression for f of x plus delta x. See, f of x we already know is right here, and that part will get plugged into my limit equation for f of x. So I'm going to plug x squared minus 3x into this equation where f of x is. But what I don't know yet is, or I haven't yet evaluated what f of x plus delta x will look like. Oh, and also a side note, if you want to call delta x h, you are welcome to do that, because I know other textbooks refer to it that way. So what I have so far is this. The limit as delta x approaches 0 of, I'm going to figure out what f of delta x, of f of x plus delta x is, minus f of x, which is x squared minus 3x, all over delta x. So what I need to do is evaluate, figure out what f of x plus delta x is. So what I have to do is take my f of x equation and plug x plus delta x in everywhere there was an x. Sorry, that should be a minus right there. So it's x squared normally, but now it's x plus delta x squared, and then it's minus 3x normally, but now it's 3 times x plus delta x. And then I need to go through that evaluation process. I need to FOIL and distribute. Also remember, x is not the same as delta x. These are two distinct variables, so they need to be treated that way. So when I'm evaluating f of x plus delta x, this is what I get, all of that. But I noticed that, actually no, nothing can combine or cancel. So I'm going to plug all of this into my limit. So here's what my limit now says. So it's the limit as delta x approaches 0 of all of that minus the f of x that we had substituted in earlier. So all of that has to go right here. And then all of that is being divided by delta x. So now I'm going to do some simplifying in the numerator. I am going to, well, distribute first of all, which will make this negative x squared and positive 3x. So I notice right away the 3x's will cancel and the x squareds will cancel. Okay, that's good. Simplifying already without me having to really do anything. Now what am I left with? I have 2x delta x plus delta x squared minus 3 delta x. All of that is being divided by delta x. Okay, but now I notice I can factor out in the numerator a factor of delta x. They all have it in common. And why is that so nice? Because then that can cancel with the delta x in my denominator. And by the way, let me point out, that's where the 0 over 0 was, right? Because delta x is going to 0. So it turns out all along there was a common factor of delta x in the numerator and denominator, and that is now gone. So I can plug 0 in for the remaining delta x in order to evaluate my limit. So I get 2x plus 0 minus 3, which gives me my derivative for this function. So the equation 2x minus 3 is my derivative of this equation f given earlier. Let me put that back in my answer. It was 2x minus 3 is our final answer. But this process that I used to arrive at that answer is just as important as the answer itself. Having that foundation of knowing where these derivatives come from. So what this function is, this is the collection. You need to understand this. This is the collection of all the slopes of all the tangent lines. All the lines that were tangent to f at every single x. At all x, right? That's what this is. To find a slope of any particular tangent line at x, I just plug x into this derivative, and that'll tell me the slope of that particular tangent line. Because what is this? This is the collection of all the slopes. This is the slopes. That's what this is, as its own function. That's what the derivative as a function is. So in part B of example 2, I wanted you to also, see what happens when you have to deal with a fraction for your function. Well, I still start out by writing the same limit definition. So it's good to have this formula or definition memorized. So we're always letting delta x go to 0, and we always have a delta x in our denominator. And in the numerator, we have these two different y values. One evaluated at x, the other one evaluated at x plus delta x. And then we simplify that, plug in 0 for any remaining delta x, and what that will give us is the derivative. It'll give us the slopes of all the tangent lines at all the different x's. Okay, but let's go ahead and plug in this function for f of x. So remember, whatever f of x equals, that part's going to get plugged in right there. And then what I'm going to do to find f of x plus delta x is I will just plug x plus delta x into my f of x equation where x was before. So instead of being x minus 5, it'll be x plus delta x minus 5. So let's plug all that in now. So f of x plus delta x minus f of x all over delta x. Now this is why we practiced fractions like this back in chapter 1. What I'm going to do, and again I'll show you the method I had used before, but what I'm going to do is in the numerator I'm going to multiply by all my denominators, because I'm going to basically try to eliminate the denominators in the numerator. So crazy. Okay, so I'm going to just take these two factors and distribute them to each of these fractions to simplify this fraction. Because if I can simplify the fraction, then there's a chance I can find this limit. When I distribute them to the first fraction, that denominator will cancel, but it'll leave behind an x minus 5. When I distribute them to the second fraction, the denominator of x minus 5 will cancel with this, but it'll leave behind the x plus delta x minus 5. Don't forget this was a subtraction, so that needs to be brought down. And then all of that is now over these three factors because I multiplied them to the denominator as well. So I've got delta x times x plus delta x minus 5 times x minus 5. Now what I'm going to do is simplify in the numerator. I'm going to distribute my negative 2. Don't forget to distribute the negative along with the 2. So now I have the limit as delta x approaches 0. Oh yeah, I have to distribute this positive 2 as well. Of 2x minus 10 minus 2x minus 2 delta x plus 10 all over all of that. Okay, so now I notice in the numerator 2x will cancel with negative 2x, negative 10 will cancel with 10, and I am left with the limit as delta x approaches 0 of negative 2 delta x in the numerator over all of that, delta x times all of these. And then the delta x's will cancel again because now it was just being multiplied to the negative 2. Nothing else is being added or subtracted anymore. So now it can just cancel with the delta x in the numerator, which again, that's where my 0 over 0 was, right? So that takes care of that problem. So now I should be able to just go ahead and plug in 0 for all the remaining delta x's. Oh, there's only one remaining, so that's easier. I just plug it in for this delta x right here. So then I now have negative 2 in the numerator over x plus 0 minus 5 times x minus 5. So I get negative 2 over the quantity x minus 5 squared, because this basically becomes x minus 5, and then you have like these two identical binomials. You can just say they're being squared. So again, what is that? That's my derivative of f, because this is the slopes. These things right here are slopes, right? This was a slope of a secant line at first, right? That's what this was, of any secant line at any 2 points on f. And then this limit came along. It made delta x go to 0, which made it a slope of a tangent line. But not just one tangent line, any tangent line for all x. It was a generic, we found this equation. Now we know all the slopes. They're all right there. You just plug in a given x and that'll be the slope of that tangent line at that point. We now know every single instantaneous rate of change that this function ever had. And we know it by finding this derivative as a function, which was -2 over x minus 5 squared. That is real power. I don't know if you guys realize, but you have unlocked real power by being able to find an instantaneous rate of change for this function at any x. Okay, we're going to go ahead and try this process here with the square root of x plus 1. So what we're going to try to find in this case is g prime of x, because this is g. So we'll start by taking the limit as delta x approaches 0 of g of x plus delta x minus g of x all over delta x. And like the other problems, we will sub in the square root of x plus 1 for g of x. Now, for g of x plus delta x, we will plug x plus delta x in for x inside the square root. So our limit ends up looking like this. The limit as x approaches 0 of the square root of x plus delta x plus 1 minus g of x, right, which is the square root of x plus 1, all over delta x. So this is where we have to use the process of rationalizing the numerator. Like, again, we learned this in chapter 1. We're going to go ahead and multiply by the conjugate to the numerator and the denominator. So this is why we were learning all of those processes in chapter 1 to be able to evaluate derivatives in chapter 2. So we basically have to FOIL the numerator, but don't FOIL the denominator. That's my advice. Just keep these two factors separate. So in the numerator you would get, so when you multiply these two radicals to each other, the radical goes away. And when you multiply these two radicals, you get like a long, ugly radical. And then when you multiply those two radicals, you get the same long, ugly radical, except this one was positive and that one was negative. So the middle ugly terms will cancel out. And then I'll be left with what I get when I multiply these two radicals together, the square root x plus 1 times the other square root x plus 1. The radicals will cancel and I'm just left with x plus 1. And that was all over delta x times all of that. So keep it just in factored form in the denominator. You'll see why in a second. So then in the numerator, after I distribute the negative right here, I end up with x plus delta x plus 1 minus x minus 1 all over all of this. And so in the numerator, the x's will cancel, the 1's will cancel, and I'm just left with delta x. And then that delta x can actually cancel now with the 1 in the denominator because it ends up being like a single factor left in the numerator. So actually what I end up with in the numerator after I cancel the terms and then reduce the delta x is just a 1 in the numerator. And then these two radicals in the denominator. So then I can just go ahead and plug in 0 for the remaining delta x, and I get this. 1 over the square root of x plus 1 plus another square root x plus 1. So these are like terms. There's a 1 in front of each. So I just add the coefficients, I guess, together, the 1 and 1 to get 2. So I think of this as 1 over 2 of the rad x plus 1 terms. 1 over 2 rad x plus 1. So that right there is my derivative for this square root function earlier. So it ends up being 1 over 2 times the square root of x plus 1. So those are the hardest kind, obviously. Those were definitely challenging. Now, I wanted to just show you this one little kind of side note. If you end up with a linear function, I will kind of let you cheat in this scenario because I want you to remember what the derivative is, right? What is the derivative? The derivative equals the slopes, right? All the slopes of f of x. But if f of x is linear, that means the slopes are constant. It only has one constant slope the entire time. And in this case, that slope is 3. Because I want you to know this so much, I will let you say, oh, f of x is just going to always be 3 because the slope of this function is constant, meaning the derivative, f prime, is always 3 because f prime is all the slopes are the same, they're 3. F prime of x is 3. That's the one I'll let you cheat on. That's why I put a little star there. So I have a couple practice ones for you to try on. Try to find their derivatives. Pause your video, work out all the math, come back and check it with the video. Okay, so your answer for A should be 2x minus 4. But that's minor. The main thing I want to see is if your process was correct. So this was kind of an ugly thing to evaluate, the f of x plus delta x, but I had to FOIL x plus delta x, and then I had to distribute -4 to it, and then I still have this plus 5 at the end of x plus delta x. It's just, you don't really do anything with x plus delta x, but it's still there. So all of that got written out first in place of f of x plus delta x in our limit quotient. And then I had to take f of x and subtract it from f of x plus delta x. So all the signs change, right? When you subtract, it made the x squared negative, it made the 4x positive, it made the 5 negative, which then canceled with the other 4x and the other 5 and the x squared. They all had opposite signs, basically. And that just left me with 2x delta x plus delta x squared and then minus 4 delta x in the numerator, which then had a common factor of delta x that I could factor out and then cancel with the other delta x in the denominator. Then I just plugged in 0 for the remaining delta x right here. And that's how I got 2x minus 4. For B, for the f or h of t plus delta t, I just plugged t plus delta t into the denominator where the t normally is. But then I had to subtract h of t from h of t plus delta t. So it was one of the ones with a fraction. So I just took each of those denominators in the numerator and just multiplied both numerator and denominator by them and distributed them to each of these fractions. So then in the numerator, I was left with 2t from this fraction because the t minus delta t right here canceled with that one, leaving a t behind. And then when I distributed them to this fraction, the t canceled and left behind a t plus delta t. So that was what was here, -2 times t plus delta t. I had to then distribute the -2, making it -2t minus 2 delta t, which then caused the 2 t's to cancel, leaving me with just a -2 delta t in the numerator, causing the delta t's to cancel. And then I could plug 0 in for the remaining delta t. So that happened right here and here, which ended up giving me just a t squared in the denominator. And so that was my derivative, my h prime of t. We want to use the right notation here, was equal to -2 over t squared. Now, last but not least, now that we can find slopes of the tangent lines, which are the derivative, we will also ask you to go ahead and write the equation of the whole line for any given curve at a given point, c f of c. So I thought I would give you a little formula or just a little reminder of how to do an equation of a line. So basically we use the point slope form, which if you think back to Algebra 1 days was y minus y1 equals m times x minus x1. But if you think about it, the x1 and the y1 are just a point on the curve. So we could say, so first of all, x1, we're going to call it c. And x1 comma y1, we're going to think of as c comma f of c, right? So I've got x1 is c, and then y1, sorry, is f of c. So if I swap all that out, oh, and then the slope is the derivative, right? The slope is the derivative of the function at c, so f prime of c. So if I swap all that out with point slope form, I get this. Y minus f of c, which is y1, is equal to the slope, which is the derivative, f prime of c, times x minus the x coordinate, which we're going to call it c. Now, a lot of times in textbooks, when they write out this formula, they typically write it where the y value of f of c has been added to the other side, either at the end or in the beginning. So either one of these formulas will work, right? Just depending on how you choose to structure it. But I want you to know it really just came from point slope form. And you're welcome to just go ahead and use point slope form if you would like. So like in this case, for example, this is x1 and y1, or c and f of c. What I need to find, though, is f prime of c. That will be my slope from point slope form. Now, I'm going to let you use the third alternative form for a derivative for this one because it's easier when finding a derivative at a particular point. That's the one where it's x approaches c of f of x minus f of c all over x minus c. Okay, but first I need to find, actually no I don't, it was evaluated right here. So c is -1 and f of c is 2, so I can plug those numbers in. And then f of x is this, so that's what I'll plug in for f of x, the x squared plus 1. So I'm going to take the limit as x approaches -1, by the way, because we decided, because it was given right here, that c would be -1. So the limit as x approaches -1 of x squared plus 1 minus 2 all over x minus -1. So f of x minus f evaluated at -1 divided by x minus -1. So this is a generic point on the curve minus a specific point on the curve. In fact, it's right there, -1, 2. Okay, so I'm going to simplify the numerator a little bit. So the numerator simplifies into x squared minus 1 over x plus 1. So you might say, hey, we've done this before. Yes, we were preparing you all along for chapter 2. All those limits we did where you had to factor and cancel is because we knew that it leads to problems like this where you need to find slopes of tangent lines, which require these types of fractions and then taking the limits as x is approaching c. The x plus 1s will cancel. I can plug -1 in for the remaining x. And then I get -1 minus 1, which is -2. So that's the slope of the tangent line. So if you confirm this with your graphing calculator, once I get my equation of my line, look at this tangent line here. That's definitely a decreasing slope, right? So that's why my slope is negative. Looks like it's a slope of -2. But let's write the equation of the line. Okay, so I know that my c is -1, right? That's the x1. I know my f of c is 2. That's like the y1. And now I know my slope. I'm so excited. So f prime c is -2. That's my slope. So if I do point slope form, that would just be y minus y1 equals slope times x minus x1. Y minus 2 equals -2 times x plus 1. I'll distribute the -2. And then I'll add the y coordinate over. Now, I did this in the old Algebra 1 way, but you're welcome to have the y1 added over in the beginning, like some of these formulas give us. So y is equal to -2x plus 0, actually. Looks like it has plus 0. So that's my tangent line to the curve at 1, comma 2. So here's the graph, by the way, of x squared plus 1 right here, or something like that. And then here's the point of tangency. That line would have a negative slope and it would cross the y-axis at 0. So that tells me we did this process correctly. And I have the equation for this tangent line to my curve at the point -1, comma 2. So you're welcome to use just old school point slope, or you can, if you want, make a flashcard and kind of keep these formulas, start memorizing them. They're helpful. And then f of c is just the function evaluated at x. Of course, it was given to us here. And then f prime of c is my derivative at x, and it's also the slope of the tangent line. So last thing I'd like you to do is just try this one and then check it with the video. Okay, so we already had a point on the line, 1, comma 5, which is on the graph. It's like right here-ish. And then all we needed to find was our slope, which is the derivative of f at 1. So I was using this limit form of the derivative. And I went ahead and plugged in 1 for f, that's 5. And then f of x is x squared plus 4x, and then all over x minus 1. So this really right here is just x squared plus 4x minus 5, which can be factored into x plus 5, x minus 1, so that the x minus 1's cancel. You can plug 1 into the remaining x and get x plus, or 1 plus 5, which is 6. So that's our slope. Now if you look at this graph, by the way, if you graph this equation and then graph this line, that looks right because the curve for x squared plus 4x is going up at this point 1, 5, and it's pretty steep. So it makes sense that it would have a rather large slope. Okay, so then to get my equation of the line, I went ahead and used this formula, f prime of c times x minus c plus f of c. So you can see it's kind of a nice way of doing it as well. So slope times x minus the x coordinate plus the y coordinate. And then you simplify from there. And there is our equation of our tangent line. Thanks for watching. We'll get to practice lots of this in class, and I will see you there.